Okay, so in the previous lecture on vector spaces, we looked at we looked at the idea of a vector space. We looked at the idea of a vector space. We looked at the idea of vector subspaces. And we saw what linear dependence and independence were, and we looked at the idea of span. Okay, so now what we'll do is we'll look at the idea of a basis and dimension. So if you recall from the math that you've already learned in high school and in previous courses, that any vector in R3, can be written as AI plus VJ plus CK, where I, J, and K are real numbers. We can say that where A, B, and C are real numbers, right? So A, B, and C are real numbers. So we may say that I hat, J hat, K hat, this set forms a basis for R3. So in general, how do we define a basis? If you have a set of vectors, right, v1, v2, ... vn, from a finite dimensional vector space V, then S is called the basis for V if S spans V, meaning that you take any linear S spans V, meaning that any vector, what does that mean? S spans V means that any V from this vector space V can be written as a linear combination of vectors in S, meaning that this V may be written as C1 V1 plus C2 V2 Cn Vn. And of course, and the second condition for it to be a basis is that S is linearly independent, meaning you cannot express any of the Vi, none of the Vi can be written in this form as a linear combination of the other V's. You cannot do this. Okay, so if these two conditions are satisfied, then S forms a basis for V. Now, let's look at basis for vector spaces. For different vector spaces that we've already looked at. So for Rn, a basis is E1 hat, E2 hat, E3 hat, all the way to En hat, right? So where E1 hat is 1 0 0 0. I mean, E1 hat has 1 in the first place, E2 hat has 1 in the second place, and En hat has 1 in the second and in the nth place. So these vectors, they form a basis for Rn. Why? Because notice that E1 hat, E2 hat, these are notice that this set is linearly independent 1, and that the vectors in the set, that they span Rn, right? So any anything in Rn, any vector in Rn can be written as a linear combination of vectors in S, right? A second example is that the set of vectors S, right, 1, x squared all the way to xn, it forms a basis for the vector space of polynomials of degree less than or equal to n. Remember, the polynomials of a particular degree, right, of degree exactly equal to n, they do not form a vector space. However, the polynomials of degree less than or equal to n, they do form a vector space. So for example, if we have if you have this set, right, so any polynomial from this vector space of degree less than or equal to n may be written as a0 plus a1x plus a2x squared plus all the way to an xn. Right, now notice that this is a linear combination of 1x, x squared, x cubed, etc. So in other words, Pn is an element of span S, right? Meaning S spans Pn. A third example is that the vectors. Another thing. 1x, x squared. These guys are linearly independent, meaning S is the set 1x, x squared. This set is linearly independent, right? The proof is given in Howard-Anton. Proof is included Anton's text. Another basis for R3. So the basis is the basis of a vector space is not unique. So for example, if I, j, and k form a basis for R3, so do 2i, 3j, and 5k, right? There's nothing special about these numbers 2, 3, and 5. All I need to check is that the set is linearly independent. All I need to do is check that this set is linearly independent and that this set spans R3. So these three vectors, V1, which is a 1, 2, 1, V2, 2, 9, 0, and V3, or 3, 3, 4, these three vectors also form a basis for R3. How do we know this? Well, first we check to see if we check to see if V1, V2, and V3 are linearly independent. So we need to see that the equations C1 V1 plus C2 V2 plus C3 V3 equals 0. We check to see if these equations, they yield only a trivial solution, meaning C1, C2, C3 equals 0, 0, 0. Well, we do that and we see that is indeed the case, because so we set up these equations, right? And we see that the coefficient matrix is invertible. And since the coefficient matrix is invertible, we know that the only solution to this set of equations is the trivial solution. And of course, if you have a vector on the right hand side, and the second thing we need to check to see is if they span R3. So what does that mean? It means to see that any vector on the right hand side, right, can be expressed as a linear combination of C1, C2, and C3. And indeed, that is indeed the case, right? Any vector on the right hand side, any vector v can be written as a linear combination of v1, v2, and v3. And we see that it is indeed the case, right? There's C1 v1 plus C2 v2 plus C3 v3 equals v1, v2, v3. Right? That is indeed the case, because since the coefficient matrix is invertible, and we have three equations and three. We have three equations and three. Variables. This set of equations will indeed have a unique solution. So we know that S, it spans V. Okay, now we look at dimension. Okay, so the dimension of vector space. So notice that R3, notice that Rn, the first example, right? It has n vectors in its basis. And notice that R3 has 3 vectors in its basis. Now, can Rn have more than n vectors, or can Rn have less than n vectors? Or can R3 have more than 3 vectors or less than 3 vectors? Well, this following theorem, it says no. Because if V let V be a vector space, and let S be the basis, a basis for V. Right? Remember, V does not have to have a unique basis. V does not have a unique basis. Right? If any basis satisfies the two conditions, if any set of vectors satisfies the two basis conditions, then it's considered a basis. So the theorem basically says that if any set of vectors in V has more than n vectors, meaning the number of vectors in the original basis, then that set is linearly dependent. Right? If there are more than n vectors, then you can express any of the vectors as a linear combination of the others. And if any set of vectors in V has fewer than n vectors, then they do not span V. Right? So if you have to, so you can have too many vectors. So if you have too many vectors, this leads to the problem of linear dependence. So we say that this is not linearly independent. If you have too few vectors, then this leads to the problem of this is too few vectors does not span V. Alright, so this is another problem. So you can have too many vectors or too few vectors. So the proof of this theorem is long, and it's given in Howard-Anton. So we'll skip the proof for now. Now with this, this then leads to the following fact, that all the bases for a finite dimensional vector space have the same number of vectors. Okay, so if one basis for Rn has n vectors, then all bases for Rn must have the same number of vectors. Now the bases themselves might be different. One basis might have E1, E2, E3. The other basis might have 2E1, 2E2, 2E3, and so on and so forth. However, all the bases must have the same number of vectors. And of course, this leads to the idea of a dimension, right? So the dimension of a vector space is the number of vectors in the basis of that vector space, as denoted by DIMV. Okay, so any vector space has the dimension of is the property of the vector space, right? So the dimension equals the number of vectors and the basis. So the dimension of Rn equals n, dimension of Pn equals n plus 1, right? Dimension of m sub mn equals mn. Mn is the vector space of m by n matrices. Okay, now we consider the set of simultaneous equations. Here you have 4 equations. Right, with 6 variables, right? So the solutions to these equations, I mean, if you take this matrix, 1 3 minus 2 0 2 0 2 6 minus 5 minus 2 4 minus 3 0 0 5 10 0 15, and of course 2 6 0 8 4 18 0 0 0 0. Right, so if you take this down to its RREF, all right, these are the solutions that you get. Now so these solutions, I mean, of course, there are 3 parameters here, R, S, and T. It's because only 3 of the 4 equations are linearly independent. The other 3 so you have 3 linearly independent equations, and that leads to you have 3 linearly independent equations out of 6 with 6 variables, so you must have 3 independent parameters. So the vectors v1, v2, and v3, they're of course, they span the solutions. They form a basis for the solutions of the equations, right? So they're called a basis for the null space. So S is a basis for the null space. Okay, so let's say we start with an n-dimensional vector space. Okay, I'm sorry. We are going to explain the idea of a null space later on, right? So null space. Let's just say that S is a basis for the solutions of the equations. Okay, so let's start with an n-dimensional vector space, and let's say we have a set of n vectors in that space, right? So let's call this set S. Now, if we have so since we know that the n-dimensional vector space is since we know that it's an n-dimensional vector space, we know that the basis is going to have n vectors in it, right? So we know that the basis is going to have n vectors in it, right? So now the question is, if I give you any n vectors from that vector space, right? How do you verify if those n vectors form a basis? Okay, so this following theorem actually answers this question. So you let V be an n-dimensional vector space and let S be a set in V with exactly n vectors, right? Now, these n vectors, they could form a basis, and then again they might not form a basis. Okay, so then S is a basis for V if and only if S spans V or S is linearly independent, right? So if S spans V or S is linearly independent, then S is a basis for V. Conversely, if S is a basis for V, then either S spans V or S is linearly independent. So this direct statement, right? If S is a basis for V, by definition, S must span V or S must be linearly independent, right? This is by definition. What does the definition say? That if S spans V, then S is linearly independent, and S spans V. I'm sorry. If S is a basis for V, then S is linearly independent and S spans V. Now notice that there's an and here, right? Now we know that both these statements are true if S is a basis for V, right? So then this statement, okay, so let S spans V statement A, and S is a basis for V statement V. Sorry, S is linearly independent. S is linearly independent, V statement V. And let's call this statement C. S is a basis for V. Let's call this statement C. So by the definition tells me that C implies A and V, which means that if C is true, then A is true and V is true. In that case, if C is true, the implication is that A or so then A or V is also true, right? Because for A or V to be true, then either A or V has to be true, and we know that both of them are true. For A or B to be true, at least one of A and V has to be true. But we know that both of them are true. So by definition, this statement is true. S is a basis for V implies that S spans V or V is linearly independent. Now, what about the converse? So if let's say S is a basis for, so let's say that S spans V. What happens then? Well, if S spans V, we want if S spans V, then in order to show that S is linearly independent, then in order to show that S is a basis for V, we need to show that S is linearly independent. Remember, that's the second condition in the definition of basis. Right, so we say that. So what we're going to do is we're going to prove this by. Okay, so first of all we're going to prove that S spans V, right? So first of all, we're going to prove that S is linearly independent, and we'll prove that S spans V. Then we prove that S spans V, and then prove that S is linearly independent. So so we assume one of the conditions, and we prove the other. We assume one of the conditions for basis, and then we prove the other. So we assume that. So let's say we show that S. We start with the fact that S is linearly independent, right? Let's assume that S is linearly independent. So we want to show that S spans V. Now we'll prove this by contradiction. Assume that S does not span V. In that case, then there's a V in the vector space such that V cannot be expressed as a linear combination of the vectors in S. So this implies that the dimension of V is at least n plus 1, because if it cannot be expressed as a linear combination of the vectors in S, it means that you need another vector, right? You need another vector. You need at least another vector to get to express V, right? So this tells me that the dimension of V is at least n plus 1, but the dimension of V is n, right? That's the assumption we started with. So S has to span V. Now we start with the assumption that S does span V. Okay, we start with the assumption that S does span V. However, and we're going to prove that S is linearly independent. So we assume that S is linearly dependent, and let's see what comes up. So assume that so assume that V1 can be expressed as a linear combination of the other vectors, because we said that S is linearly dependent. So V1 can be written as K2 V2 plus K3 V3 all the way to Kn Vn, where K2, K3, Kn are real scalars. Now then, for all V and V, V can be written this way. So V is an n minus 1 dimensional vector space, right? Because I could write this because I could write V as a linear combination of n minus 1 vectors, right? So which is a contradiction, because big V is n dimensional, right? Not n minus 1 dimensional. Okay, so this theorem, right, 6.616, is going to be useful later when we prove the equivalent statements about matrices. Okay, now let's look at row and column space. So at this point, what we're going to do is we're going to look at the rows and the columns of a matrix, right? And from there, what we'll try to do is we'll try to see what makes them linearly dependent, or we'll try to look at the properties of those rows and columns, right? So what we can do is we can form vectors out of the rows and out of the columns. So for example, for example, if I start with a matrix, m by n matrix A, right, and I form the rows A11, A12 all the way to A1, and so the rows of the matrix R1, R2, Rm, these are the row vectors. And these are, of course, vectors in Rn. These are vectors in and of course these are the column vectors are vectors in Rm. These are column vectors of A. So the following definition lists the important vector spaces associated with the matrix A. So if you take the row vectors of an m by n matrix, right? And you find this, and you find the span of those row vectors, then the subspace of Rn that you get is known as the row space of A. And if you take the column vectors of Rm of A, and you find the span of those column vectors, and the subspace of Rm that you'll get is called the column space of A. And the solution space of the homogeneous system Ax equals 0 is known as the null space of A. So, for example, previously when we solved these equations, if you recall, we solved a homogeneous equation. Just give me a moment. Right? So we found a basis for the solution space with 3 elements, right? So that was a null space of the 4x6 matrix, right? The 4x6 coefficient matrix. Okay, so let's look at row space, column space, and null space. Right, so for example, if A is your vector 210, 355, 471, then the rows of A are these guys, 210, 355, and 471, and the columns of A are, and the row space is spanned by these three vectors, C1 times 210 plus C2 times 355 plus C3 times 471, where of course these guys are real scalars. And the column vectors of A are 235, 157, and 051. 234. So this should be 234. So this is a typo. 234, 157, and 051. Right, so, and of course the column space of A is a set of vectors spanned by these three guys, 235, 157, and 051. So we are then interested in the following questions. What connections, if any, exist between the row space, column space, and the null space of a matrix? And what connections, if any, exist between the solutions of the equations Ax equals V, right? Where A is an m by n matrix, x is an n by 1 variable vector, and V is an m by 1 constant on the right hand side, and the row, column, and null spaces of A. So you start by considering the general matrix A, B, and of course the variable matrix X, and you take the columns of A, C1 to Cn. Now notice that in the column picture, so you have x1 c1 plus x2 c2 plus xn cn equals v. This is the column picture. This is the column picture of the solutions, right? So B has to be some linear combination of the columns of A for the equations to have a solution, right? And this is what we saw in the column picture before. So a system of equations Ax equals V is consistent if and only if V is in the column space of A. Meaning V can be expressed as a linear combination of the columns of A, right? So that's what it means to be in the column picture, in the column space of A. Now notice that this theorem is just another way of talking about the solutions in the column picture, right? So if, for example, if you have a coefficient matrix A, minus 1, 3, 2, 1, 2, minus 3, 2, 1 minus 2, right? And you take the first column to be u, the second column to be v, and the third column to be w, then the solutions can actually be written as, and you take v to be 1, -9, -3. You can write the solutions this way, right? So this is column 1, column 2, column 3. U is column 1, column 2, column 3. And if you recall, this is how you looked at the thing in the solution in the column picture. Now here's a very important problem in vector spaces, in the theory of vector spaces. Suppose I give you a bunch of vectors in n dimensions, right? v1 all the way through vn, right? So if not just a bunch, I give you n vectors, right? N vectors, right? So the question is, you don't know if they're linearly dependent. Actually, it shouldn't be a bunch of vectors. Okay, so this n, right? This n is not necessarily the same as this n, right? So this should be v1, v2, vr. So this is a typo. The thing is, I don't know if they're linearly dependent or independent, right? And I don't know how to find a, and I need to find a basis spanned by these vectors. Now notice that if we are in n dimensions, let's go. I mean, this should be VR, right? So if we are in n dimensions, and if r is greater than n, then this bunch of vectors, right, is linearly dependent, right? Because the number of vectors is higher than the number of vectors is greater than the number of dimensions. So let's see if let's see how we can verify. Let's see how we can find a basis for the space spanned by these vectors, right? So in order to solve this problem, we look at a bunch of properties of the row, column, and null space of a general m by n matrix A. So start off with the equation Ax equals 0, right? The 0 vector. So in augmented form, you can write it this way: A and 0 vector on the right. So if you do the if you take them into the RREF, you get R0, because remember one thing, that the right hand side is unaffected by the elementary row operations, right? So hence the solutions to the equations Ax equals 0 is the same as the solutions to the equations Rx equals 0. Right? So we have come across something very important, that the null space of any matrix is unaffected by elementary row operations. The null space of any matrix is unaffected by elementary row operations. Null space meaning the solutions of Ax equals 0. So what does the next theorem say? The next theorem tells you that the row space of a matrix A is unaffected by elementary row operations as well. And of course, this is something that you need to prove in the assignment, that the row space of any matrix is unaffected by elementary row operations. Now, why is that the case? And for this, you have to, of course, use m by n matrices, right? In general, m by n matrices. Now, it may be tempting to conclude from the above that the column space is unaffected by elementary row operations. However, that is not the case. Of course, that is not the case, because consider the matrix A, which is given by 1, 0, 2, 2, 1, 1, 1, 1, minus 1. So in the RREF is this, right? So this is the RREF. So the vector space spanned by the rows is the space spanned by 102, 211, and 11 minus 1 is the same as the vector space spanned by 102, 01 minus 3, and 000. Because notice that the third row is the difference, the third row is actually equal to the difference between the second and the first rows. Okay. However, the space spanned by the vectors, the column vectors 1, 2, 1, 0, 1, 1, and 2, 1 minus 1 is different from 1, 0, space spanned by 1, 0, 0, 0, 1, 0, and 2 minus 3, 0. Right? Because notice something here, that this third column equals 2 times the first column minus 3 times the second column. Right? So the third column is not linearly independent, right? It's linearly dependent on the first and the second columns. Now, so what has happened here is that the space spanned by these 3 columns is different from the space spanned by these 3 columns. Okay, so now we look at how to find the null space of a matrix, right? So imagine we have this matrix, this 4 by 6 matrix, right? And we want to find the solutions to AX equals 0. Right, so because we have 3 linearly independent equations in 6 variables, we should have 3 free parameters. And the null space is the space that is generated by this basis of vectors, right? So R times some v1 plus s times some v2 plus t times some v3 plus some constant gives you the null space. So this is actually this actually gives you as you vary r, s, and t, and then you add this first constant column vector, you get solutions. You can generate solutions for AX equals 0. Okay, so these guys, they form a basis for the null space of A. Now let's look at another theorem. If a matrix R is in its row echelon form, then the row vectors with the leading ones. Okay, so now how do we find a basis for the column space? Right? How do we find a basis for the column space of a matrix? The first thing we need to do is we need to take the matrix. First step, take the matrix to the RREF, the reduced row echelon form. Now, once you do that, right, once you take the matrix to the RREF, the row vectors with the, according to this theorem, the row vectors with the leading ones, they form a basis for the row space, right? And the columns that contain those leading ones, they form a basis for the column space. So so for example, if okay, so this is the proof, right? We'll skip the proof for now. Let's call it proof optional. You can go over the proof if you want to. You can ask me questions. It's just simply counting zeros and ones, right? So let's say I have a matrix in its RR in its row echelon form, right? In fact, now notice where we have leading ones here. We have leading ones where in fact this should be 0. Okay, this element here should be 0. So because it is above a leading one. So this is in its reduced row echelon form. Reduced row echelon form. So notice that the last row is made up entirely of zeros. So R1, the first row is 10503. R2 is 01300. The second row, R3, is 0010. And of course R4 is 0000. But that's irrelevant since we're not taking 0 rows into account. Right, so notice that the first column, the second column, and the fourth column, they all have leading ones. Right, so the first, second, and fourth column, they form a basis for the column space of the matrix. The first, second, and the fourth column. So this is a 4 by 5 matrix. This is the first, second, and in fact this should be the fourth column. They form a basis for the column space, and the first, second, and third rows, they form a basis for the row space. Remember, the rows with the leading ones and the columns with the leading ones form the bases for the row and column space respectively. Okay, so now we go back to the original problem that we posed at the beginning of the chapter, right? So let's say you have a bunch of vectors, right? And you have R vectors in n dimensions, right? So we want to find a basis for the space spanned by those vectors. So what we do is we form the matrix A whose columns are the vectors in that set, right? And then what we do is we reduce that matrix to reduced row echelon form, RREF. So then we're going to get the vectors W1, W2, Wn, right? So, and then we look at the columns that have leading ones, and those columns are going to give me a basis for span S, right? A basis for the space that is spanned by S. So now let's look at rank and okay. So examples are actually given in your there are examples given in your in the examples in your assignment, right? So let's look at rank and nullity. So the row space of R equals the number of vectors in the column space. So number of vectors in the row space of R equals the number of vectors in the column space of R. This is something we just saw, right? And there is no, however, and this is no coincidence, right? This is always the case. So for example here, you saw that the row space of R contains 3 vectors for this matrix here. So the row space of R has 3 vectors and the column space of R also has 3 vectors. So this is no coincidence. So because the dimension of the row space, because if a column so the number of rows that contain a leading one is of course equal to the number of columns that contain a leading one, right? So the dimension of the row space must be equal to the dimension of the column space, and elementary row operations do not change the dimension of the row space and column space. What they do is they only show you the linear dependence relations. So hence we have the following theorem. So if R is any row echelon form of A, right? If any row echelon form of A, the dimension of the row space of A equals the dimension of the row space of R, and the dimension of the column space of A equals the dimension of the column space of R. And therefore, we have the following theorem, right? That we have the following definitions of rank and nullity. So the dimension of the row space of A, which is equal to the dimension of the column space of A, is known as the rank of A. And the dimension of the row null space of A is known as the nullity of A. So if you start off with a matrix, 4x6 matrix, and then you take it to the RREF, then the two basis vectors are the ones, and the two basis vectors for the row space are this one and this one, right? And of course the two basis vectors for the column space are this one and this one. And if you solve AX equals 0, you get the dimension for the column space of A, right? Dimension of the null space of A, right? So the nullity equals dimension of null space, and rank is the dimension of the row space and column space. So notice that this is the rank of this matrix is 2, rank of A equals 2, and the nullity of A equals 4. And rank plus nullity gives you 6, right? Rank plus nullity gives you the number of columns, right? 6 columns, right? And this is in fact the next theorem that we'll look at. If A is a matrix with n columns, then rank A plus nullity of A equals n. So the proof is this. Now if A has n columns, then AX equals 0 has n solutions, right? Now some of these columns have leading ones and the others don't. If you take A to the RREF, right? If you take A to the RREF of A, then some columns will have leading ones and some won't. And those with the leading ones correspond to solutions without parameters, and the ones without leading ones, the columns without leading ones, they correspond to free parameters, right? So the number of leading ones plus the number of free parameters should give you. Now the columns that have leading ones, the number of columns with leading ones, that gives you the rank of A. All right, so number of columns with leading ones, number columns with leading ones, that is the rank of A, right? And number of columns without leading ones, that gives you the nullity of A. And if you add rank and nullity, you get the total number of columns. Okay, so using this, we can actually expand the equivalent statements for square matrices to 15, right? So we began with 7. The 8th statement is that the column vectors of A are linearly independent, right? The ninth statement is that the row vectors of A are linearly independent. 10th statement is the column vectors of A span Rn. 11th statement, the row vectors of A span Rn. 12th statement, the column vectors of A form a basis for Rn. 13th statement, the row vectors of A form a basis for Rn. Notice that all of these statements 8 through 13, right? From 8 to 13, they follow from theorem 616. So if you have n vectors, right? The column, and remember the REF is the identity matrix, right? Now, if that is the case, then obviously the column vectors of A are linearly independent, right? And because if they are not linearly independent, what's going to happen, for example, if you can express the column vectors of A as a, if you recall that if you can express one, if you express one, let's say if you can express one column as a linear combination of other columns, right? So what's going to happen is that you will get to a point after what's going to happen is that you'll see that the determinant of A is going to be 0, right? So this means that the determinant of A equals 0, because what's going to happen is you will see a row of zeros in the RREF, right? Row of zeros in the RREF of A. So if you see that, then you know that the determinant is going to be 0. Okay, so statements 8 through 13, they follow from theorem 616 that we proved before. Now, how do we show that statement 2 implies statement 15? So if Ax equals 0, right, then and you have a if Ax equals 0 is the only solution, has only the trivial solution, because then the nullity of A is 0, because there are no free variables, free parameters, remember, and no free parameters left to form a basis for the null space, right? And since we know that rank of A plus nullity of A equals n, and if nullity is 0, then rank of A has to be equal to n. So that proves our 15 equivalent statements for square matrices. All right, you will learn more when you do the